All right, so let's review the irrational numbers. If a number is not rational, we categorize it as irrational. More explicitly, any number that cannot be expressed as the ratio of two integers is regarded an irrational number. Examples of irrational numbers are the square root of 2, Euler's number, and pi. This is an unbounded set, so there are many, many more of these. Theorem 2. The square root of 2 is irrational. So let's work through a pair of standard proofs regarding this proposition. And we'll use a method called proof by contradiction. So inversely to the proposition, suppose that the square root of 2 were indeed rational, which would imply that it may be expressed as a ratio of two integers, p and q, as follows. So we'll go ahead and set up the equality inside of a LaTeX environment. Now this proof involves two computational steps and two implicit steps that we'll go over in just a moment. So the first step is to square both sides of the equation, and the second step requires disjoining the fraction by multiplying both sides by q squared. So the purpose of step A is to eradicate the level-lateral side of the equation and to distribute the exponent on the dextrolateral side. In step B, we simply disjoin the fraction by multiplying both sides of the equation by q squared. Great. So per theorem 1, p and q up to the order of their primes, and this phrase, up to the order of, is a somewhat standard phrase commonly used in mathematics to mean in all cases except. In essence, what is meant here is that the prime factorization of an integer is unique in such a way that we are discounting the permutations of its factors over commutativity as distinct. In other words, we are enumerating those permutations as one prime factorization. But this will become more clear in just a moment. So per theorem 1, p and q up to the order of their primes, each has a unique prime factorization. Okay, so each has a unique prime factorization, which is to say that p squared is equal to quantity, the product of its prime factors, times quantity, the product of its prime factors, of which there are n in both cases. It follows that p squared has an even number of prime factors, and so does q squared, regardless of the number of factors composing either integer. And once again, how do we know this? Well, we know this because in squaring p, we are simply doubling the amount of factors, of which there are n to begin with. Well, this, however, contradicts the equation derived in step B, as the left side of the equation would have an even number of factors, while the right side would have an odd number of factors in its respective prime factorization. Clearly, there's an extra factor in the value of 2 here on the right side of the equation. Therefore, our assumption that the square root of 2 is rational must be ejected as invalid. Okay, so that constitutes the first proof. Let's do another one. All right, proof 2. So the premise p squared equals 2q squared implies that p is even. So this is one of the two implicit steps that I mentioned before. And we'll take it for granted, but essentially, if a number squared is even, as implied in the premise p squared equals 2q squared, then the value p is also even, as a result of biconditionality. Conversely, if a number p is even, then p squared must also be even, again, as a result of biconditionality. In the particular case where p and q are mutually prime, q is necessarily odd. And this simply follows from the fact that we have just established that indeed p is even. Moreover, the square of an even number is divisible by 4. Well, this is the second implicit condition that we're going to take for granted. Suffice it to say that an even number n is defined as 2 times some number k, and if we parenthesize that number and square it, the resulting value would equal 4 times k squared, in which case n, or n squared, rather, would be divisible by 4. And by the way, in my shorts catalog, you can find proofs of both of these implicitly assumed propositions. Okay, but clearly, 4 does not divide the following value. And all we've done here to derive this value is we've taken the right-hand side of the equation of the premise derived in step B, and we've substituted for q the definition of an odd number, as we understand q necessarily to be an odd number, which would imply that q must be even. Since 4 does not divide this squared even number, q must be even. And of course, that would produce a contradiction of our preceding stipulation regarding q, where we have taken q necessarily to be odd. And so we're done. All right, so hopefully those 2 proofs are clear and helpful. So if you like the video, please give it a thumbs up, give it a like, and don't forget to subscribe to the channel. And if you have any questions regarding the math or the LaTeX, please comment in the comment section below. Hopefully I have answers. And I'll see you in the next one.